Let's get started with sharing the screen. Um, let me show you, let me get rid of that. So let me show you projects first. First project I want to show is this one. Like I remember I said this in the beginning of class, right? Personally, I'm a backend developer in terms of my own personal career. I don't really care if there's a button look green or purple or whatever. That's a front end job. But I still pick out this project because I just really appreciate what this person did in terms of the design. Um, if you look at the files, it's just what we talked about previously in class. Like we previously talked about how you make API call in TinyTroop. That's a built-in package, but TinyTroop doesn't do a whole lot of things. It only does text in, text out. And then if you want to customize it, then you do this kind of Streamlit application, which we previously talked about. It's called dual agent simulation. Um, so um, I really like this one because essentially what the student did is on top of the question and the answer, the interviewer and interviewee relationship, they also did a judge, and then they also did a humorist and a statistic guru, which I thought was pretty interesting. And then this simulation can continue, pretty much carry out same flavor as what TinyTroop did, except that there's more agents around TinyTroop. Does that make sense? TinyTroop, the agents you have to design customize, like you have to customize it one by one. And then what the student did is essentially give you all of that right off the box. Um, so um, even though I care more about backend, but what this project showed me was you should probably also care about front end, because if you present things this way, it's very intuitive. And then you can continue the conversation until the simulation ends in the end. You get the idea. So if you pull this off in a final project, obviously, it's going to be a good grade, right? Because it demonstrates you understood everything, and then you have your own implementation, and then you have your own agents, and then you're able to say a few things about them. Now, of course, this covers the presentation of the final project. I'm going to obviously ask you questions about what you did, right? If you can't answer any of this, then that means you did not do this. But I'm assuming you did this for now. And then if you're able to do this and answer all the questions about this app, then your final presentation should be like pretty good to go. Like it should be very close to A+. So if able to do this, perfect, no problem. You're gonna get good grades in this class. So that's one example, right? One example means that I take what's in class and then I do something on my own. This is an example of that. So that's number one. Number two is this. This is actually a complete back-end design. If you look at the directory, it's here. So there's a lot of things packed into this. So for example, there's models, and this models means that this student showcase that there's a Keras model that you can fine tune, and the model's living in this directory. So you can very much customize it however you want. So this directory shows me that the student understood that. And then on top of that, there's Python script in here, there's data in here, there are logs that show me that you thought about how to cache your data in the backend. Great, I want to see that. If you thought about that, that's a great indication that you have the mindset of working in the industry. And then app.py, that's just a main script helper, things like that. And then README requirements. Requirements, of course, important. It shows me that you understood CI/CD is important, and then you can basically control the package version. So if you have requirements.txt file, then it allows developers to do the QA/QC. So all these things are important. If you lay out the structure, it showed me that you understood what it takes to be a backend developer. So even if this model is crap, which I don't think so, but even if this model is crap, and let's say you train like 5 epoch, it's like complete pure garbage, doesn't matter. Like I know that you did it, I know you can do it. To get this model performance high is a matter of GPU, right? But if you're able to lay this out, then that goes beyond what just to buy expensive GPU. Make sense? As a contrast, this is a good grade. This is also a good grade. But these two repositories are tackling two complete different problems. Does that make sense? So if you're able to see that, and then if you're able to absorb all that information, then that's good with me. Does that make sense? So obviously, I cannot use the same judgment for this to judge this, right? it makes no sense. One is front end, one is back end. So that's that. And then last thing is this one. This one is also very interesting. This kind of design really showed me how you make progress from deliverable 1 to deliverable 3, in the sense that you're able to show me what is it that you did in deliverable 1 and how you can learn from that, right? I think most of the people submitted either a notebook or some sort of Python script. And then the notebook and Python script are run through of pretty much the coding class. So if you do that, so if you can do that, that's great. As I said, like if you do exactly what I did, like exactly means no more, no less, like exactly what I did in class, you get a B plus like out of the box. But if you want to go above and beyond, and then you want to improve the theoretical component, then you want to do something like this. Because this really show me you're essentially able to dive into your own code and make improvement out of that. So that's very important for me. And then this allows me to judge that you actually learn something and you're able to make changes on your own work as time progresses. Does that make sense? So I will consider this also like an A+ project. Any questions? Okay, so these are all open source, by the way. So obviously it's open source, it's online, right? It's not like secret or anything. So obviously, hopefully these things can provide inspiration for you guys in terms of your own project. And really just dive into, don't worry about what I want or what other students are doing. Just focus on what you like. That's really important. Focus on what you like in the project. What wakes you up in the morning? You want to hand on to that inspiration. And then if you're able to show me what that is, then that's going to be very important. And trust me, like, once you did it, I'll be able to see it. It's very obvious because I've been doing this for many, many years. And like if someone wakes up thinking about a problem versus someone just trying to meet that deadline, those two submissions is going to be very, very different. Um, yeah. And same thing goes with in the industry, right? If you're interviewing for a job, really show people that there's something that you like, versus it's just a deadline for you. Like it's very obvious. Like I've interviewed so many people in the past. The attitude is really it makes a difference. I don't know how to explain it other than it's important. But you want to show, you just want to show that, and the best way to experience that is find something you like. It could be anything. Like the best way I can explain it is like a soccer game. Like when I was young, I played soccer, and then if there's a game coming up, I'll wake up like 6 or 7. I'll just automatically wake up before the alarm, and I'll get myself onto the field and start playing soccer. So you want to find that inspiration somewhere in here. Does that make sense? Cool. Any questions? Awesome. So with that being said, these things are here. They're online. Feel free to take a look. Next, I'm gonna move on to API. So the most the bulk of a project in the end is going to depend on how you can wield the API call. The more API call you can wield, and then the more fancy of API call you can wield, the more powerful your agent will be. And then what I mean by that is, let me show you guys a couple of things. First thing I want to show you guys is something like this. Let's see. Yeah, this is public. Okay. And then where did I put it? I think I put it somewhere here. Okay, so let me start with this system architect. This is a template. There are a million ways to implement this, right? There are a million ways to implement this. You can break this down to front end, back end. You can do this complete in Python, complete in back end. You can mesh this entire thing in an API call. You can do whatever you want with it. I'm gonna try to dive in every single building block and explain to you what need to happen. Like what need to happen when we say agentic AI, right? So you start with this. So first of all, you start with a conversation. User is on your chatbot, is talking to you, right? It's talking to you. So conversation start with the user, and then user said, I want to do something. So on ChatGPT, it kind of gives you this illusion of you can say whatever you want. That's only on ChatGPT, right? In the industry, this prompt is going to be very much guardrailed. You can probably say like 5% of what you can say, and that's pretty much it. If you're asking for a joke or say something wrong or racist or whatever, obviously those things are all taken down. So what I mean by that is whatever user says, the first thing you're gonna hit is LLM, and then this LLM has intent classifier. You can call that an agent. I call it agent, but it's really just a function. You can think about it as function in the backend. You can think about it as even a classifier, like some sort of a sentiment analysis classifier. You can even build this on BERT using Hugging Face, right? To classify this prompt goes into this LLM. It's an actual API call that's in your system, or it's just someone's chatting with a chatbot, right? So that's the number one thing you can do. And then this kicks off the following back and forth. If it's just chit-chatting, then you just bounce that back. You don't even hit the end of the cycle. You bounce that back to the user and be done with it. But if it is an API call or a functional call, then you want to kick off this self-correction cycle. And a self-correction cycle start with dependency resolution. So if it's functional call, you go in here, and then you ask yourself, what do we need to make this API call? So that's what this dependency resolution agent is doing. Why is this important? You're going to need this eventually. It might not be obvious for you, but you're going to need this eventually. What I see online for most people do is they use LangChain or use LangGraph. LangGraph has this thing built inside, but it doesn't tell you how that's done. So if you have a generic function, LangChain will probably take care of it. But if you're working in the industry that your API is extremely complicated, this is not going to cut it. So somewhere down the road, LangChain is not going to cut it. And if LangChain is not going to cut it, then this box, you better be able to handle that yourself. Does that make sense? So this dependency resolution is essentially another function that look at your API and say, okay, this API is good to go. We can make this API call. Or the dependency resolution is going to say, wait a sec, we need XYZ from to basically call this API, but we don't have X, or we don't have Y, or we don't have Z. So that's what dependency resolution agent is doing. So either you have everything or not. If you don't have everything, you then bounce it back to gather everything, right? And then this there's a third thing here called librarian agent. Librarian agent is essentially another function that looks at your database. You can think about this as a RAG algorithm, retrieval augmented generation. But in reality, this librarian agent is essentially a mapping function to see if the existing information that we require for this API call already has been shared in a historical conversation. If it's shared in the historical conversation, let's fetch that. If it's not, then let's ask the user, right? So librarian agent can take care of that. So these two things, typically people miss out on that. Because if you do LangChain, LangChain has this built-in as a generic function. You don't see what's inside of this if you just use LangChain out of the box. So that's why I want to bring this up. And then this librarian agent also resonate with what this student is doing. So let me give you, excuse me, not there, this one. So what the student doing logger, that logger essentially is where librarian agent sits in. Does that make sense? If you're gonna build your backend and you're gonna build a backend completely 100% all by yourself, like without LangChain, you're gonna need some sort of logger, and the logger cache the data, and the data sets the scene for this librarian agent to basically swim in and then to see if the data is present. If it's present, great, let's grab that. If not, then let's ask the user, right? So let's say information 1, 2, 3. If you have 1, 2, but you don't have 3, but you also need 3, then what are you gonna do? You bounce it back. You bounce it back, send that question to the user, say, hey, could you provide us a third information that's required in this API call, whatever that is, your name, address, whatever is required for that API call. And then you should know what these things are because you are the one define each and every single API call. If you don't know what it is, you should probably ask another person on your team, the designer. If this is blanked out for you, then obviously something's wrong, right? Obviously the cycle cannot be complete. So assuming that you know every single parameter goes into that input payload of the API call, then you want to collect that, and then the user say, okay, my name is John, I live in whatever, 123 Drive in New York, and then that conversation gets bounced back past the classifier, and then gets sent into the payload. And then now you have everything complete, then you can make the API call. So you bounce this back, and then you finish the API call, and then once you finish the API call, you finish the program, you send the response back to the user. Does that make sense? So that's the general logic for agentic AI framework. It's essentially a function call built inside of a chatbot, and that function call, you have full control of what that function call does and how to invoke that function. Any questions? Okay, perfect. I have a framework in here in this repo that already does this. You can take it to go, or you can do it yourself and do it better. What I did it's I have a very linear thought when it comes to this kind of stuff, meaning that if I tell you X, I'm going to do X. Right? I'm not going to tell you X and do Y. Right? So, but of course, in your own situation, it might be different in terms of what you're doing. So let me show you guys the code just a little bit. So to pull that off, you need to have a couple of things. Number one thing you need to have is some sort of metadata. The metadata composed of a couple of things. Can I make this smaller? Well, I'll just scroll up and down. So metadata looks like this. Let's say you have API that send a message, right? You can call it send underscore SMS. Let's say that's an API call. In your metadata, you need to store the information of what the trigger word is, and then what is the sample payload, so that the function can, so that when the intent classifier realize that the user wants to send a message, the agent can then come in here and fish out the required payload, which is the name and the message. If you're gonna send a message, you better say who you are, and then you better tell people what the message is, right? Let's say those two parameters are the most basic ones to make that API call. Then these key are saved in the metadata so that the agent knows what to look for. Okay, so the metadata has to exist. It has to exist in some sort of form. It might not look like this dictionary, but it needs to exist somewhere. Does that make sense? So that's essentially what I mean by metadata. It's kind of like a bridge between natural language and the schema of the API call. Okay, so that's one thing you need to have. The other thing is obviously you need to define a function yourself. So here I have a list of APIs. For example, send a message, it's a function. It's a generic Python function, right? DEF, send SMS. And then I require, and then this template, you need to make sure that every single function is the same. This is to make your life easier. If this input argument is not the same across all the list of APIs, then you're gonna have to basically have a giant code to handle that, to handle the dependency of the dependency when the chatbot is running. So that's very cumbersome. You're better off just make this payload exactly same every single function. Does that make sense? So then the only thing you're changing is this payload. But what's going into these APIs are exactly the same. Okay. And then inside this payload, I can then check the name and the message body. And then the name and message body, well, I know what these things are in terms of requirements for this API call, because that information is in the metadata. And metadata will specifically look for these information in the conversation history. If they don't exist, then we need to ask the user, what do you want? Like, what's your name? Like, what message do you want to send? Does that make sense? And only those two information are filled in or present somewhere in a conversation can then allow me to send this API call. Otherwise, you're just going to be a bug. Make sense? And then this is obviously a generic one. You guys get the idea. Instead of sending a message, you can, of course, do a list of other things. It can be a logistic regression, linear regression, pretty much all of the machine learning model that we talk about in this class. This is just Python code, right? I mean, you can just from scikit-learn import logistic regression, right? And then instead of the name and message body, it can be just X and Y, right? Because to run logistic regression, you have to have X, you have to have Y, right? So you guys get the idea. That's why this is structured in this way. And then there are some declaration things, like for example, this is a declaration in Python class object. You can make sure. So this register function is define a helper script that tells computer that I want this function to be an actual function. Like this send SMS is a name of a function. It's not like a random string floating around in your chatbot. So you have a list of API, and then you have the metadata. The rest of the work is essentially looking things up from one place and then match it with what the user is talking about in a conversation at a different place. And if those two things match, then you can make an API call. So any questions about this? Great. So now we talked about list of APIs, right? Now the next step is how do you do APIs, right? There are two ways to do API. One is to do it locally using fast API, and then the other one is doing it on the cloud. If you do have AWS account, then obviously do it on the cloud because that's a more professional way to do. And I'm going to explain how do you do that. The most easy way is use fast API. So what I mean by that is this is the website that does fast API. There's a fancy tutorial here that you can start with an example, which is here. So this script is actually already ready to go. You can literally just copy this and then save it in like a main.py somewhere. Right, so I already did this. I'll show you guys what that looks like. Can you guys see this? So you just need a main.py. That's pretty much it. And I can show you what that look like. This is exactly copy paste from here. Everyone see that? I didn't do anything fancy. I just create a main.py script. I just copy paste everything here, right? That's all you need. And then in terms of the package, I already I'm already in the virtual environment. So this virtual environment doesn't really have anything other than the fast API. This is all you need to install. So let me show you the what did I do here? I think I just did this one line of code. There isn't even a requirement file that's required. You just pip install fast API standard, and then you get that a list of pip package. So you get a list of this thing if you just do pip install fast API. And then how it works is you have this script, and then you run it using fast API CLI. And then what's going to do is it's going to stand up these two functions in support of that API, right? And this is a local API, meaning that you can only hit this API if you are inside this computer right now. Like if you are running the same IP address on your computer right now, even if this turn on, it doesn't work. So let me show you how that works. So all I need is this thing, fast API dev main.py. So you want to make sure you're in the correct environment and directory, and then you do fast API dev main.py. It's gonna kick off an API, and this is gonna look like this. It means that this API is now up and live, and it follows this IP address, right? HTTP ://127.0.0.1, and then the port range is 8000. And notice that there's no S here. Like if you add an S, doesn't work, obviously. So I can click on this, and it's gonna basically show me this payload. And this payload is coming from, let me show you. This payload is coming from here. Does that make sense? Because if my API doesn't have anything behind, it will just return hello world. It says here, it's defined there. However, if my API has a bunch of other crap behind, like for example, /item /whatever, then it's gonna grab the things in that item and then concatenate it here and then return something else with it, right? So let me show you what that looks like. I think they have a endpoint here you can click on, this one. Let's say you do 5. Let's say you do 5, and then your query is some query. Then you will render this. why would it render this? Because in my function, I define it as the query is XYZ plus 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 whatever the Q you enter. And then all that thing is getting returned in that dictionary. So this API, you can keep hitting it, right? Just like that. You can keep hitting it. It will just give you this. And you can type in whatever you want, like this. It will just render that all together in that one API call. So when people say making an API call, we're talking about, so API stands for Application Programming Interface. So you are interacting with the software, you're interacting with the program using a live URL. And in this case, the live, it's a fake live because live is only locally in my computer, right? And this 127 endpoint is a local endpoint. Any questions? Okay, so if you don't have AWS, right, and then you only have like some model locally. Let's say you download like a BERT model from Hugging Face or whatever, like Gemma 3 from Google, from Hugging Face, right? You can use Fast API to stand up an endpoint, and then you can hit that endpoint in your agent. Make sense? Any questions? So to take that home, what I mean by that is this function here, right? This function here goes in your chatbot, can very easily just be sitting in one of these. I mean, it's just a function, right? We're just talking about a function. So the function can very much just be sitting in here, and then you can basically become an endpoint locally in your computer, and you can hit that endpoint in a Streamlit application as if the Streamlit application is only a front end implementation, and the back end are all just a list of APIs. Any questions? Okay, so if you're doing this completely locally, as what I just did, obviously this terminal window is occupied, right? If this means this is up and running, and it will continue to run unless I shut it down. Okay, so if I Control C, I get out of this. Now this is exit, right? I stopped it, right? And then now you're hitting this. Obviously, I don't think it's working. Yeah, so it stops working. And then the good thing about this is you have a local API, don't have to pay anything. The bad thing about this is the occupier terminal. So for now, this is no big deal. But if you're loading a Gemma 3 in here, that's like 27 billion. And then let's say your computer doesn't have a high enough of a GPU, this will probably be a problem. Because your presentation is very short, right? Like I'm not having you do a presentation that's an hour. Like your presentation should probably take like 3 to 4 minutes, right? Obviously, whatever you're loading, better be able to finish in 3 to 4 minutes. Like if you're loading a Gemma 3 27 billion or like Llama 3 that's 700 billion in your local environment, then obviously it's up to you to check that infrastructure in your computer can load this thing. You're not punished if you can't load a large model, right? As long as you load a model and you can demonstrate me that you understood the API, then you're good to go. Yeah. Yeah, you can use the together. Yeah, of course. Yeah. This is just purely for knowledge. Purely for knowledge. Yeah. Okay. So that's so up to here it's completely local, right? Now I'm gonna show you the professional way to do it in terms of using AWS. On AWS, you want to start with something like a Lambda function. So I go to Lambda, and then I'm gonna give a name. Let's say I'm gonna call it basic API tutorial test 2. And then for framework, I'm just gonna pick Python because that's the most popular language. And hit create a function. So in the industry, whenever you need to stand up an API, the conventional way will be to go through Lambda. It's not required. There are other things you can front it with API. Lambda is just the most basic one. So right off the box, Lambda function is going to give you something like this. This is the main script goes inside of the Lambda function. As you see here, it's Python. Of course, depending on your usage, like for example, I speak Python, then obviously I choose Python as my main language. If you prefer Java, then obviously go Java or whatever other language you want. And then this is going to be a generic call of the Lambda function. You can save it, deploy it, and then you can run through a test. In this case, this payload doesn't really matter because I'm not getting anything from the body of the event, right? So this payload doesn't really matter. I'm just gonna save a test one and I'm gonna invoke it. You're just gonna get whatever the response that's defined here back from the event. So this is essentially a small script on AWS that's executed within a Lambda framework. Now what you want to do is front it with an API call, or also known as a trigger. So how it works is you click on trigger and then you check a source. What we're going to demonstrate is the second one called API. You can actually design whatever you want and hook up with your Alexa device if you want to go that way. It's actually possible. People pull that off before. I've seen it. It's actually pretty cool. So API gateway, and then what I'm going to do is create a new API. And then here's when things get a little bit interesting. If you're going to do everything complete from scratch, you go to the first one. If you want to have something that's just like good to go as a template, the easiest one is actually REST API. So I'm going to hit that. And then since there's nothing in a Lambda function right now, I'm going to make this security open. And then, but I am going to assign an API key so you guys get a full experience of what that feels like. So I'm going to hit add, and then this is going to add an API trigger that's invoking this Lambda function. And then I need to do a few things. I need to go in here and then make sure that API is deployed. Right now, it's not deployed yet. So you go into API. This is now outside of Lambda, right? It's not in Lambda anymore, right? This is now in API gateway. So we're talking about a particular resource in API gateway. So now what you do is you can, of course, test it. I always test it. And then typically I go with post method. Post method, it's just a habit from working with large language model. If you're working with database, let's say I'm just getting the data from the database. I'm not sending anything to anywhere, right? Then you're gonna do get method. Post method means I'm sending a payload somewhere, I'm getting something back both ways. So a payload in, payload out. So if you're doing that, then you're doing a post method. In some other scenario, if you are doing like if you are just uploading a data, like let's say I don't care anything back. I don't want anything back. I'm letting the user to drop a PDF on my cloud, right? In that case, you do a put method. So these methods do change depending on the business requirements. But the most simple case is just a post method. Worst case scenario, you just don't send anything in the payload. So post method, and then this can be pretty much whatever you want because like as we said in the code, we're not grabbing anything from the body. So this can be whatever you want, type XYZ, and then you're gonna get that JSON payload back with the 200 response. So that means it's hitting the Lambda function correctly. Now you want to stand up an API. And the way you do that is I'm going to set the API key to be true. So I do want to require an API key. I'm going to explain why this matters in just a sec. Just bear with me, and I'll explain why this matters. So if I set API key to be true, that means I cannot physically invoke the API unless I put an API key in the payload. So that's what that button means. Now I'm going to deploy this API. And then I'm gonna pick a new stage. And then if I'm just developing anything, I'm just gonna call it dev. In the industry, there's dev, there's sandbox, there's also prod. Typically, there's 3 environments. So hit deploy. Now this invoke URL, I can then take it to go. And then let's say post, that's the invoke URL I want. And then I can go to Postman. I'm gonna put it here. If I change this to post, this doesn't really matter because it's not grabbing anything from the body. ABC, ABC. If you hit this, I want to show you guys what it looks like. So you're gonna get something like this. This means this API is stopped. Like on the server side, it forbids you to make this API call. Why? Because you have not attached API key to it, right? So let's attach API key to it. How do you do that? Well, you do that by creating API key and creating a usage plan. On AWS, API key alone doesn't really matter unless it's associated with a usage plan, right? So let me show you what that means. So usage plan, and then I'm just gonna do this basic one, and then I'm gonna add a stage, which is a stage I just created, test two, and then I'm gonna hit dev, add to usage plan. And then now this test two API, it's being added to this usage plan. And then this usage plan actually has a rate of 10 requests per second. Burst, I think burst is like the number that you keep hitting and then until it times out or something like that. Quota is how many you are allowed to hit every month. So why do these things matter? Well, it matters if you are, let me show you this. So OpenAI platform, things here. So if you go to OpenAI and then you obviously API keys here, we talked about this last time. This limits, these things are what's controlling the cost structure of how much of the API product that you can use. So in today's world, and obviously it's not like today's day one that this exists. This exists many years ago, but it made it. But OpenAI made it famous, right? So conventionally, you have you're selling goods, right? I'm selling a Tesla car, right? I'm selling you a good. You pay me money, or I'm selling you a service. Like for example, I serve you a sandwich, right? Selling you a service. Today's world, the most common product in the tech world is API. So you're selling API. So API it's essentially a tech service. So I'm serving you a model without telling you what's in the model. And frankly speaking, you don't care because you just want to give me data and you want some response back, right? So how do I price that, right? The pricing strategy comes in the token limits and the rate of request. And then in this case, they also have batch. But essentially, these things are pretty much related to how this usage plan is created in the backend. So someone somewhere in the company have to go to the math and say, okay, 10, 20, and 1,000 is a perfect combination if a user pays $9.99 per month. If a user want to pay $20 per month, then we can give them maybe 2,000 quota or 3,000 or 4,000, whatever, right? So that's how the math works. So someone look at this number and then look at the price and then say, this is the point that maximize your profit. Then that's how those numbers are determined. Okay, so this is a requirement for you to associate a key to the API, right? So end of the day, once you go through this math, you have your API key. You can attach this API key, and then you can come back to this API call. You can go to header, and then you can add in X API key, put it here, and then this should be able to work. It might take a few it might take a few tries, but eventually it will work. Okay, so there we go. Does that make sense? So this is a live API call. So if I just send this to you guys right now in your own computer and I leave this on, you guys can hit the Lambda function. And you guys get the idea. This Lambda function can pretty much be whatever you want. Does that make sense? It can be a large language model. It can be grabbing something from your database. It can be an agent. It can be whatever you want. So if you do have AWS account, of course, you can pull all that off for a final project, and that's going to be a great project. If you don't have this, you can do through Fast API, pretty much exactly same, right? Fast API, you also have a script locally like this. It's a same logic. Any questions? Any questions about API or how that would use? Okay, perfect. Yeah. Yeah, that's a good question. So Hugging Face has a token, and that token acts as a key. And that Hugging Face has the package. So in the sense that, let me go to Postman. So this, you can build that into a Python package. And then that Python package, you can make it pip installable. So user don't really have to remember what this is. No one's gonna memorize that, like FV2W, like no one's gonna memorize that, right? You can build that into a Python function, and then a Python function can be like some fancy name from transformer import whatever, like auto model or something. And an auto model, you enter like a string of the model ID, and then that's how they get away with it. But Hugging Face, it's not. It is open source, but it's not complete. Like it's guarded by the key, by the token, right? So there's something behind it. Yeah. But yeah, that's a good question. You can then wrap this in a Python function, call a nickname or whatever, put on PYPI. So PYPI means something like this. Here, like put on here PYPI. There are like million tutorials on YouTube to teach you how to do this. By the way, like it's not that hard. You just need a token. The same thing. You just need a token, and then you can push whatever Python package you want on PYPI and make it pip installable. Yeah. So yeah, that's a good question. If you want to do that, please go ahead. It will only add bonus to your project, not gonna subtract that. Any other question? Yes.
And the function will be a code for gives us a machine learning code, right?
Yeah.
Gives us a machine learning code.
Yeah, absolutely. So in your function, which I'm hoping, so to his point, yes, you can, like if it's just a generic large language model, you can use Together AI, you can use OpenAI, make that API call directly, no problem. I'm talking about like a actual model, like for example, from scikit-learn import logistic regression. Obviously, that function doesn't exist unless you define it, right? So yes, to answer your question, some sort of ML function has to be required because at the end of the day, this is a data science class. So it doesn't have to be. I'll just use logistic regression as an example. One of these agents. Let me go here. So one of these lists of functions in your pipeline need to have some sort of machine learning behind the scene, right? And then you can stand that up using a fast API if you want. Let me think about how to let me say this. If you want to design a function as a helper function in the backend, you're gonna make it work. Like what I have here, you're gonna make it work. It's just that if someone else did the fast API, then obviously they get a little bonus. Does that make sense? Because that's more work to do that. Does that answer your question? Yeah. Any other question? Okay, perfect. So wrap up the first hour. Number one, obviously API call, local on the cloud. You need to understand both. You just need to do one. Right? You don't need to do both. You can, but you need to understand both, right? Second, one of the API calls has to be data science related. It cannot just be like send a message or something. It has to be some sort of data science related API call, meaning that you can consume the data. Here's X, here's Y, and then the function will build like logistic regression for you, right? Or whatever, like decision tree, random forest, neural network. I'll leave it to you what you want to do, but you need to at least have one. Cool. Yeah, I'll stay here if anyone has questions. But yeah, let's take a break. Let's come back at let's do a longer break. Let's come back at 7:20. Let me share screen, and then let me go to the slides. Okay, so previously we are at deep learning, and then I think we already talked about all of this till the end of RNN. So let me go there. Here. So neural machine translation, we talked about that last time, right? It's essentially two RNNs, encode, decode, take a sentence, and then it comes out a sentence. And then what it's predicting is the next token, but it's in a different corpus. Like English has an English corpus, French has a French corpus. It's predicting the next token in a different corpus. And then someone figure out if you do it this way, you'll be able to get the accuracy pretty good. So that's essentially one baby step on top of RNN. And then on top of that, this is kind of like graphical interpretation of what that next token prediction look like. So you're predicting the next word just like that. This is the trajectory, or also you can call it journey of LLM. In the beginning, I would say something like this, it's still important. But right now, these techniques, such as bag of words, are now all replaced by transformer. It's not to say bag of words is not important. It's important. It's just now all that it's done by another layer in a LLM, and that's pretty much it. So the I would say you can use attention layer as, excuse me, attention paper here as like a loose cutoff. Like you can kind of say pre-attention layer, it's looking like this, and post-attention layer, it looks like this. And most of the modern day LLM design, it's some form of attention layer. There's like fast attention layer, there's like quantized version. DeepSeek has its own multi-head latent attention layer that they somehow hit some of the layers in the attention layer, right? It's a different basically massages of what attention layer will do for you in your model that you can play around. So the after attention layer, the most important one I would say it's BERT. BERT means bidirectional embedding. I don't know what that R stands for. I need to look this up. I kind of forgot about that. BERT stand for. What does BERT stand for? Bidirectional encoder representation from transformers. So that's another application of transformers. And then after that, it's pretty much GPT. So GPT actually came out in somewhere between 2018 and 2019. And after that, pretty much all different forms of LLM started to show up. When I was at Columbia, it's somewhere here. And when the attention paper came out, we all saw it. And then it was actually quite interesting because we kind of know that this thing is powerful, but we didn't know that OpenAI has that much data. So that's kind of like the shocking thing. It's not attention layer itself. The shocking thing is how OpenAI get their hands on that much data. That's the shocking thing. At the academic environment, you typically won't be able to pull that off with the funding that you have in school. But that's just the nature of difference between academic world and the industry. So no one's at fault. Just want to say that the important is data, right? The important is not this thing. This is important by itself, but data is more important. So that's that. And then it starts with a bag of words. Bag of words, as its name suggests, you're taking a couple of words together as input. Like for example, there's a cute dog, or my cat is cute. While you pick the 4 words together as input. Right? So that's kind of like what that is. And then you encode, right? You create tokens, not based on my as one word, but based on my cat is cute as one thing together. So that's bag of words. And then so this is how before ChatGPT, before attention layer, this is how people take care of like short-term, long-term memories and things like that. And then the rest of word is easy, you just rely on RNN. The embedding, people quickly figure out, token doesn't carry semantics. Token, it's saying this is the index that this thing is in the dictionary. Whatever that thing is, it could be 2 words, 3 words, 4 words, bag of words, right? Whatever that thing is, that thing has an index in a corpus, and that index is a token. So token is essentially a one-one map. It doesn't have semantics. The embeddings have semantics because embeddings are matrix multiplication and the matrix are learned. It's a learn from the data. So if you take the embeddings layer, and then next chapter we're going to talk about VAE, autoencoder. So if you take the embeddings layer, you can then run autoencoders, and then you can check out the cluster of all of the sentences. And the cats and dogs are going to be in one cluster, and then like fly or moon or airplane is going to be another cluster. It's because the semantics are indeed captured by the embedding layer. So the only thing important about this slide is there's difference between token and vector embedding. Vector embedding carries the semantics, tokens does not. Okay, So end of the day, all of the things that we're talking about falls under this world of representation learning. Or if you build a model, it's a representation model. So representation learning, it's different from conventional machine learning. Machine learning, it's referring to something like support vector machine or logistic regression, that's machine learning. Representation learning means that you are representing the data in a different form, and then you're learning that instead of learning the original data, right? Why do I say that? Well, the magic all comes from this embedding. Um, if you can figure out the best embedding out there, then it's like pretty much half the work is done. It's all done by the embedding. So that's the same thing here. I'm not like I'm not learning my cat is cute, right? I'm not learning that. I'm learning the vector representation of that input sentence. So that's why this whole framework is called representation learning, or also representation model. Here are a couple of examples, right? You can input document, you can input sentence, right? You can input words. You can even put like it's not written here, but you can even input like hashtags or whatever, like sound or music, same thing goes, right? All those things are passing through some sort of embedding model, and embedding model give you a vector, and that vector carries the semantics of what the input is. Now, of course, people are now going to ask the question, okay, what are these semantics coming from? The answer is they come from training data. Ideally, you collect enough training data to represent the entire human knowledge. Basically, what that means is you scrape the internet. Um, that's easier said than done, but let's say you've done that. Let's say you scrape the internet, you spend a lot of money, and then you get the internet data. Does that really mean that the embedding is correct? Or does that mean the embedding is just a general norm of what 7 billion people believe out there? But then the question is, are you going to believe what 7 billion people believe in or not? So that raises so that structure by itself raises a lot of problems, right? People are gonna say, well, I don't believe in what the other people believe in. Well, that's fine. You can make that argument. But the difference of the domain comes into play of how do you want to fine tune large language model. So when people say fine tune large language model, most likely people are talking about um, how I feed the same model a small domain of data so that now the semantics can be updated, not based on the internet data, but based on whatever the small domain of data that I wanted to believe in. Of course, the assumption there is you already saw the data in this domain and you are expert in this domain and that you believe in this domain, right? So if that is the case and you have that confidence and you've curated the data yourself or you have your team curate the data for you and you know what the team is doing, then you have a confidence that, okay, let's change the semantics of the model based on that small domain of data. Here's another thing to think about. You can think about it as Venn diagram. So this is the original data that the foundational model has already seen, original data. And then you can think about the circle as basically internet data, right? Now here's your own data in your own domain. So here's the problem. Where is the second circle gonna be, right? If you are fine-tuning a large language model, that's just like basic, let's say it's a primary school math. Obviously, primary school math is on the internet, and internet chances are already saw that. Your domain is probably not that different from the internet data. So in that case, I would say it's gonna look like this, right? This is your data, so this is yours. Or conventional, or as a separate example, I'm gonna use a different color. Let's say you are some math expert that there's like a certain proof that somehow only you're the only one that knows how to solve it, and no one else on the internet knows how to solve it. And you have been keeping it pretty secret, and you have not said anything to your student, you have not said anything to anybody else, and you have not said anything on the internet. Let's say internet doesn't know that, right? In that particular case, I will argue that the Venn diagram probably look like this. So this is that math genius that somehow knows a certain proof that no one else knows. So in that case, I would say that Venn diagram is probably just going to be two circles that don't even touch each other, right? So Obviously, these are two extreme cases. So if I'm going to annotate it, so you can say this is a primary school math. So primary school math, and then this is some higher level math, very advanced. Does that make sense? The area of the overlap of the Venn diagram dictates how different the semantics is going to change in the embedding layer after fine tuning. Any questions about this? Okay. So if you want to be really, really, really rigorous about it, the actual math goes something like this. You take a look at the token that can be scraped from the internet. I think it's something like a billion or something, like in the billions, somewhere in the billions of token. So you can look at this size of a token, and then whatever token size that you're having, you also count the token of that. And then there's some sort of distribution that you can work out to tell you exactly, like if it's in this case, exactly what the area is. If it's like 1% or 2% or whatever, 3%, you can work out distribution and then see how the percentage of the overlap is. And then you can pinpoint the size of the training data that you need. So of tokens give you like a rough estimate, not exact, but like a rough estimate of how big the training data need to be. So I'll give you an example. Let's say original data is 1 billion, and then let's say let's make it very easy to understand. Let's say this is 1 billion, and this is also 1 billion. 1B, and then let's say this is also 1B. Let's say this magical professor somehow wrote like a billion token of math proofs that's like in his basement that no one else knows, right? In that case, I would say, too bad. I'm very sorry, but to fine tune this large language model, you need to give me all your nodes. Otherwise, it's not going to work. Does that make sense? The other way also makes sense. The other way also should make sense. That's the easier way. So if I have a primary school math that's like coming from like 20 problems, like some very small example, like something like this, like the circle looks like this, very small circle. Like you count token is probably like 1,000 tokens. Well, 1,000 compared to a billion, it's not so much of a token, right? It's like very small. It's almost like a few, like you can just ignore that. So if that's the case, then I would say not so much fine tuning is needed there. Does that make sense? So that's the contrast. And then most likely in the real world, it depends on what team you're working for. If you're working for a team that's working on a legacy product, the knowledge is probably going to get lost. If the company is like 30, 40 years, I would say in that case, you want to have as much data as you want. But if a team is hiring you that's a startup that's looking at public data out there, then I would say not so much of a fine tuning it's required. Does that make sense? Okay. Let's get rid of this. Cool. So all that said, embedding layer is the most important thing, and then it allows you to kind of roughly guess what's the training size required if you're going to fine tune your own large language model. This is a transformer layer. As you can see, it pretty much is a same structure as if I scroll up to this, like from here, from neural machine translation. It's a very similar structure to transformer. The only thing different is instead of RNN, transformer use attention layer. So attention layer, depending on, well, there's so many different form of attention layer. The easiest one is self-attention. Self-attention is essentially probability to go from yourself to yourself. That's kind of like the easiest way to interpret that. If you learn, I mean, I don't know if anyone here take that class, but if you take I think in statistical inference 1 or 2, this is assuming that in a stats department and the class follow the structure of the stats class. Typically in inference class or apply probability, they're going to teach you this thing called Markov chain. And then behind the Markov chain, there's this concept called transition matrix. The transition matrix is essentially what goes behind the self-attention layer. So what it's doing is something like this. It's calculating the probability from one word in your corpus to another word in the same corpus. right? So number one thing you have to be aware it's the same corpus. Like these three words is the same as these three words. There's like a fourth column here, obviously it doesn't work. So that's one thing. If you have the same three words as rows and as a column, what that means it's also symmetric. So all that properties in transition matrix all apply here. Markov chain, transition matrix, all that thing symmetric, all that thing applies here. So what that means is this. What does this box mean? So this box means the probability go from row to column. The row you can think of as I, index I, column you can think of as index J. So it's a probability from I to J. So mathematically, if you want to write that out, it goes something like this. So probability from I to J, and this is going to be a percentage. Like for example, I'm going to make something up. Like for example, this is 10%, something like that. And then because you have a whole dictionary of words, obviously this matrix, like in reality, this matrix is going to be very long, like very big and very, very wide. It's going to be a box, right? Because it's symmetric. And then these words need to be unique. And then the probability essentially tells you from one word to the second word in the matrix, what is that probability? And obviously everything sum up to be 100%, right? Because it's a percentage. And then on top of that, what I can also tell you is, um, the most accurate large language model is able to basically get that accuracy, get that percentage to be very accurate, and come up with words that very 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 much resemble that of a training data. Does that make sense? It's not like the large language model all of a sudden start loving things, right? There's no emotion here, right? And large language model only know the next word is llama after love because in your training data you have that sentence repeated in that pattern many times, and that large language model pick up on those patterns. Does that make sense? Large language model has no clue that you're loving something. Okay, so people online freak out about this. It's just a pattern in the training data. So let me erase that. So long story short, self-attention basically give you probability. And that's pretty much it. It gives you a probability. And then you use those probabilities to do whatever it is you need to do. If it's dense layer, then you feed that into a dense layer. Of course, someone magically cook up with something else, which next slide I'm going to introduce. But essentially in the attention layer, and if you only just zero in on attention layer, that probability is what we're interested in. So after attention layer, obviously you want to do something with it. So in terms of transformer, they also are using another language that's essentially doing the same thing, except that in this case, it's mask. The reason it's mask is because they're designing the matrix in a way that you don't necessarily know what the next word is, or sometimes the sentence in the middle is blanked out. And the reason that's the case is because we are trying to guess like what each thing is in that corpus. And you are not really, like, you don't really know it's exactly the next thing. So that's where the mask is coming from. Because you can curate training data in a way that the mask covers up the correct next word. And in this case, this in English, love, it starts with letter L. So letter L, LMN, so somewhere in the middle of a dictionary, right? But here, this letter might be a different place in a dictionary. And that mask can tell us where that place is. So after that, if you look into this, it's exact same thing, except that the outside of the matrix is blocked out, it's blanked out. So with that being said, that's pretty much the architecture of transformer. On the internet, I think there's so many tutorials about transformers out there that's doing a good job. The one I really like is there's someone to the GPT, I think it was GPT-2 or something, visualization. Let me see if I can find it. If I can't find it, then I'll send you guys a link. Let me see if this one. This one. So this is a visualization for there's a nano GPT, which is smaller. There's GPT-2 here, which is obviously longer than this thing. So you can click on that. That's GPT-2. It's like much longer. And then nano GPT, it's much shorter comparing to that one. So you can actually read into this and then read it paragraph by paragraph, and it actually has examples to explain to you what each layer mean and how the math play out. So it's very much not a black box. Like we know everything in here, right? Obviously, right? Someone already coded this thing, so obviously you know everything in here. But some people out there still argue that this is a black box, not because mathematically they don't know what it is, but because we still couldn't unpack how the semantics translate from one layer to another. Like, sure, I know the math here is a matrix. You just do a matrix multiplication. Fine, that's fine. That's not what they're arguing about. They're arguing about the semantics. Like, for example, if you say, let me find a good example. Let's say this is my sentence. I love llamas, right? How do you go from tokens to the next word? How do you go from a token of love to the next word of token of llama? And how does that and why does that matrix have to work that way? That much it's still not very clear for pretty much everybody out there. It's not very clear from like first layer all the way down to somewhere down here. So no one can really explain. People can explain the math, but no one can really explain semantically why each layer has to design this way. For people to argue that semantically this is how we guess next word. So that much is not very clear. But mathematically, if you just ask me to write a mathematical expression of how the model works, we know everything in here. Does that make sense? That's the difference. So that pretty much takes us to the most recent couple of years, which is all of the popular models out there. They're coming from various different of companies, starting with ChatGPT, obviously. And then very quickly we have Llama. The only difference is open source and proprietary. Open source means you can download the model artifact. Model artifact is on Hugging Face. I mean, you just physically download token, you physically download the model, you can run inference. You can run a prediction. People like usually when developers test out their concepts, their proof of concept, they will probably start with open source just because just because it's quick and dirty, and then you get your hands on something, you build the prototype, and then you hand over to like a beta customer, and then see how they like it, right? In your presentation in the end of the class, it's going to be very similar to it's going to be very similar to what that process will look like in the industry. So you quickly build up a prototype, and then you give a presentation. In this case, to me, that you say, hey, here's a user journey. Here's what this chatbot will be doing, and then here's why I think the solution will work, right? So it's very much similar to that. So presumably, most students out there will probably use open source, right? Now, taking the one step into the future, if you show to your stakeholder, right? In this case, let's say you show to me and I say, great, I love it. I'm willing to pay for it and take it to production, right? That's when you start going from the bottom to the top. So from bottom, you get a stakeholder buy-in, and then stakeholder says they like it, and they're gonna stake your project, they're gonna support it. Then you're gonna go through all that API stuff. Build the API, come up with the usage plan, go through the math, figure out numbers, right? You build up API, and that API you can hide it behind a firewall, and that firewall you need some sort of payment, right? Just like what OpenAI is doing. So that will take you from open source to proprietary models. So the trajectory should be something like this. You're swimming down here, swimming down here, swimming down here. Somewhere down the road, you're like, okay, this worked. I got it. Like I built this model. I know it worked. I present to XYZ and they all love it. Now let's take it to production. If that's the case, you're gonna jump on here, jump up here. Any questions? It should be pretty straightforward. Okay. So anyhow, I'll give you guys an idea. Gemini is from Google, Growth from Twitter, but now it's known as X. Claude is from Anthropic. Palm is from Google. Bard, I think it's retired now, but it's also from Google. What else can I tell you? Falcon's from AWS. Quen is from Alibaba. Llama is from Facebook, or known as Meta. Phi is from Microsoft. So most of these models out there are pretty much doing similar things if you're just talking to it. If you're doing code generation, I think some of these will probably play out well. Mistral and Claude are, like in my personal experience, are pretty good with code generation. Mistral's here. They also have a 7 billion one here. Claude is here. Quen is from Alibaba, so unless you can serve the model completely behind your firewall, you're probably not going to get past the cybersecurity team in your company. So because Alibaba is a Chinese company, so you can test it, no problem. But I have not, like, I don't think I've sent any proprietary data to Quen at all. So that's the difference. Gemini is from Google. Phi 2 from Microsoft, it's actually only 2.7 billion. It's actually considered, I mean, in 2024, 2.7 billion is considered a small language model, but 5 years ago, it's going to be a large language model. So in terms of today, not 5 years ago, in terms of today, if someone give you a 1 billion parameter or 2 billion parameter large language model, it's small. It's just quote unquote small. Okay, so let me give you a couple of more concepts before we wrap things up. I said earlier that transformer has different style, right? Like makes sense because someone come up with the attention mechanism concept. Obviously, a whole lot of people is now gonna want to improve on it. So reasoning is one big thing that's pretty much being done and continuously being done in the past couple of years after transformer layer. And in terms of reasoning, it's like this: the machine still doesn't really think about reasoning as what humans do. There are a couple of ways to do this. The easiest one is you have this tag called reasoning or tag called think or whatever. These tags tell the large language model that this portion is the think portion. That in the training data, when you curate it, you need to have that tag think and then the reasoning spelled out in the training data. So it's not the same way as how humans think about reasoning. So in some sense, you can think about it as still text generation. I'm still guessing the next word. It's just maybe the next 20 words is a paragraph that's reasoning that might not lead to the final answer. Does that make sense? So it's as if before I give you the final answer, I'm giving you a paragraph to explain how that got to the answer. So that's the easiest way to think about it. So the way to do that, the way to do that, or the best way to do that, in terms of this paper that they're trying to present here, it's the positional encoding. Positional encoding helps you to train that part of the reasoning that people realize is very helpful. And then all the way go to 2024. I believe this is a paper from Facebook that they realized that you can actually introduce this RMS norm. It's a normalization. It means root mean square error. That's what RMS mean. It means root mean square error normalization. It's a special type of normalization that they introduced to the layer output from before they enter that into the self-attention layer. So in a way, what that means is, remember the stock price data that we talked about before? Don't let it go to infinitely high, right? Because stock price always go up. If you look at the stock price in the 50s, is all like $10, $20. But if you look at stock price today, it's like thousands of dollars. It doesn't mean the model you build is wrong. It just means the distribution has changed across the time. So the same thing here. What a normalization doing is to kill that trend of a change and make sure everything is scaled to like the same distribution. So you can kind of think about that. So this kind of allows your self-attention layer to learn the previous output more efficiently. So that's what that means. So I think this is probably the last thing I want to talk about is the fancy thing that DeepSeek has come out. So DeepSeek has come out two things, right? Number one is self-attention. They're able to do it in a latent, in like a, they call it multi-head latent self-attention. So what that means is this is mask. That's it. Nothing special about that. This is actually something special that DeepSeek is doing. It's called mixture of expert, or sometimes if you hear MOE, that's what that stands for, mixture of experts. So mixture of experts, how it works is it's essentially each expert is a neural network model. And then neural network model, we already talked about before, is just a generic dense layer in a TensorFlow package. You can think about this as, and they might have different dense layer, like expert number one might have like 4 dense layer, expert number 2 might have 3 dense layer. You get the idea, right? And then you can have expert 1, 2, 3, 4, 5, 6, 7, 8, something like that. Obviously, the more experts you use, then the more parameters that you have in the model. So dense layer, that's not very special. What a special thing doing is they actually have a router that they put in the MOE before they send the data to the experts. So now this is actually a novelty here is they actually build some sort of a conditional probability estimator into the MOE layer such that it's actually able to guess, okay, this embedding, this vector from embedding layer, expert number 1 should probably take care of that. Let's just send to expert number 1 and ignore 2, 3, 4, 5, 6. So they're actually able to come up with something like that. And this router is trainable based on your data. So what's the benefit of this? The benefit of this is it turned out that when you run inference, you're only running inference a quarter of the parameter. So that's how they're able to cut the cost down and cut the speed up and increase the speed. Because in a conventional transformer layer, every layer it's a matrix as a whole, and we're not like no one's talking about conditional on whatever. Like you have a vector of information going into the layer. That's it. You hope for the best, and hopefully you guess the next word accurately. But in this case, they're able to say, okay, hold on a second. In this layer, I'm only going to use 25% of the parameters, and the other 75% I'm just going to ignore. So that's what's interesting about this router. And then that's actually never been done before. So that's a novelty there by design. And I think that's after that, it's pretty much it. After that, you get the idea. This whole thing can be a layer, and pretty much everything we talked about before applies. You can stack this. You can have skip layer, do the jump thing, right? Everything we talked about before now all apply. But this layer by itself, it's a unique design. Yeah.
So those experts are.
That's a good question. I don't know how they did it I don't think that's being discussed. I might have to read the paper better to know that. I did not notice that part of in the paper, unfortunately. I think there's definitely an argument of the first team that pulled this off. Obviously, it has to be trained. They don't have a pre-frozen layer to work off of. But once DeepSeek come out with that first model, you can then take the DeepSeek artifact and model weights on Hugging Face, and then you can say, okay, expert number 1, I love that very much, but expert number 2, 3, 4, those are garbage. I'm gonna fine tune it by freezing this and then get the other experts up. Totally, no problem. Yes, correct. You can do that. Another argument you have to be aware of is the purpose of this router is to say expert number 1 is great, and I'm going to ignore 2, 3, 4 because the probability of going to expert number 1 is high. If you get all the other experts to be the same level as number 1, then there's no point for this router to exist anymore because they all give you 25%, 25%, 25%. So in that case, then it kind of defeats the purpose of why do you even want them at the first place? Yeah, so I don't know if that's being discussed in the paper. I might have to dive deeper into the paper. But theoretically, yes, you can freeze a layer, you can train the other one, get the other performance up, do whatever you want. The other thing is these experts can also be domain specific. That's another interesting about this is if you get these experts to be domain specific, you could really have it's kind of like a step towards AGI, which is you can have one model that this guy draws a picture, this guy translate, and this guy does whatever you want to do. But then this is actually all in one model. So that's an interesting point. I don't know if anybody is doing that right now. But this opens the door for that. Does that make sense? Any other question? Okay. I have a little bit of pros and cons here to summarize pretty much everything we discussed. These are pros and cons in terms of in terms of complexity of the model and like speed of inference and things like that. It's a loose summarization. In the real world, I think it'll probably be domain specific. This slides I kind of just pull off from that paper down there. But in the real world, I think it would probably be domain specific in terms of pros and cons of all these fancy LLMs. I think that's pretty much it for, yeah, that's pretty much it for today in terms of slide. So what I'm hoping to do is give you guys enough material till, let's see, today is Tuesday, April 1st. Be aware that next submission it's in 2 weeks. Okay, so it's not next Tuesday, right? It's next Tuesday, so 15th. Does that make sense? In 2 weeks. I'm gonna type out an announcement to tell you guys exactly what the expectation is. But honestly speaking, it's gonna be pretty much depending on your own project at this point. And then from my end, I'll say this. So just make sure everyone's on the same page. You are better off to have a user journey predefined. Like, for example, this user doesn't know anything about data science. He's gonna start a conversation by saying something like, I want you to build a logistic regression using housing price or something like that. Right off the bat, that sentence is probably a little bit of a problematic, because how do you define logistic regression if the target variable you're trying to predict is price, right? So how do you resolve between what the user is asking and what your API is allowed to run, right? Everyone here knows logistic regression. Everyone here knows logistic regression is as simple as from scikit-learn import logistic regression. And you give X, you give Y, it will give you the answer. Yes, we all know that, but that's not the problem. The problem is the user doesn't know that. And you have to make the assumption that if that's the assumption you're going for, user does not know that. If user does not know that, how do you resolve in between what the user wants and what the chatbot, what your API is allowed to run, right? So right off the bat, I can think about the following scenario. Let's say I'm a user. I'm on your chatbot. I say, give me a logistic regression to predict housing price. You should not be hitting that API. Like, you should be saying, okay, I look at the housing price data, and the housing price is a continuous variable. Would you like me to turn them into different categories for you before I run logistic regression? If I say yes, then you guys better have an agent that's kind of like running like the basic distribution on the housing price and say, okay, if you break the housing price down to $10,000, $20,000, you're probably gonna get like equal distribution, 30%, 30%, 30%, and then maybe you're gonna get category 1, 2, 3 equal weights. So then you're gonna come back to the user. You say, okay, I've broken down the housing price to 3 boxes, to 3 categories. Are you okay with that? Are you okay for me to run logistic regression on this target variable? User said yes, and then you execute the API. Does that make sense? And then the API will spit out some sort of performance metrics, which next class we're going to talk about that. There's like a list of performance metrics that you can produce. You can have an AI judge to rate this performance. Of course, you can also present this to the user and ask them if they're happy with it, right? So all that's up to your own design. I don't want to put too many constraints on how you guys design chatbot, as long as it makes sense, right? So number one thing I will say is user journey. The easiest way for you guys to do is pick one user journey. Like your chatbot needs to solve one problem that's related to data science, and that's it. There need to be some sort of a natural language interface, meaning that you talk to it, right? And then the chatbot is then carry out some sort of function that's related to some sort of machine learning machine learning algorithm. Does that make sense? And then the second thing I would say is don't try to solve all of the problems. Take one user journey, make one assumption, and go from there. Because you can always iterate on top of it. So in regard to that, what I'm planning on doing is the next submission will be in 2 weeks. So not the 8th, so the 15th, right? And then 15th, you should be able to have like a workable, some sort of workable chatbot. It could be on Streamlit application. It could be just like some sort of terminal window. You can talk to it back and forth. Whatever you like. I don't want to put too much constraint on UI because this is not a front end class, right? This is a data science class. We worry about data science algorithm. If you can make it pretty, obviously that's good. But you're not penalized by not making it look pretty. It can be a chat. It can be a terminal. In a notebook. It could be in Colab. It could also be a Streamlit application, right? That much it's up to you. There's no requirement. But the requirement is there need to be some sort of large language model inside. There need to be at least one data science algorithm, whether it's decision tree or logistic regression, that's up to you. And then you need to be able to resolve it. So if a user asks a question, say, if a user is smart enough and say, I want to break the housing price down to 3 baskets and run a logistic regression, and the 3 baskets are category 1, 2, 3, and then the features are whatever, number of bedrooms. If a user is smart enough to do that, then there's no point of anything, right? Then the user can just do that. So there's no point of anything. So typically, user journey is you assume the user doesn't really know what data science is, right? So everything that we talk about in this class, how do you curate the data? How do you check the rows and columns? How do you do logistic regression? How do you do linear regression? Decision tree, support vector machine, right? All those things apply here. And then you don't have to do all of them. You can just do one algorithm. Does that make sense? So once again, 3 things. Take a user journey. You need to have a LLM and at least one machine learning algorithm. And then more importantly, how do you resolve the situation where user doesn't know what they're talking about? So any questions? Okay, good. So that's going to be submission on Tuesday of April 15th. And then let's hit that goal first. And then hopefully I'm going to give you guys some feedback based on your submission. And then next class come back, I'm going to introduce more tools. And then after April 8th, it's pretty much going to be very open-ended. Like it's going to be like most of the class time I want to dedicate to projects, and I want to pretty much allow you guys to ask any questions you want. So 15th and 22nd probably it's going to be very much open-ended, and then the end of a and then 29th is the final deadline for the presentation. And I haven't hashed out the exact time yet because they're like 20, 30 students. I don't want everyone to get crammed in one Zoom session. So maybe I'm going to break it down to 2 or 3, something like that. And then you just pick the hour that worked the best for you. Does that make sense? I'm going to try to do it in the evening. So during daytime, like no one's like occupied with something else. And then hopefully that will work. If it doesn't work, then obviously I'll find out time to work with you. Does that make sense? So loosely speaking, expect the deadline for the next submission to be 15th, and then you have another 2-week work off the improvement of your project, and then by 29th, we're gonna find some time on Zoom, so we can do the presentation. I'll give you a highlight, but just everyone's here. Like I'll tell you, presentation is going to be expecting 3 to 4 minutes to walk me through what your app is doing, what your chatbot is doing. You tell me what the user journey is. You show me you can talk to it, and then you show me that the chatbot will talk back to you. And then with another 3 to 4 minutes, I'm gonna ask a couple of questions, just so I can kind of test you on like do you know? Are you truly First of all, did you build this yourself? And then, do you understand the code that you're doing? Right. Any questions? Okay. So the presentation should be every person expect like 6 to 7 minutes, no longer than that. Cool. Any questions? Okay, awesome. I'm gonna stay here for a couple more minutes just in case someone have questions. But in terms of today, you're good to go.